All right, forget everything you think you know about math homework, because today we're not doing homework. We're playing a game, and it's all centered around one kind of quirky prime number, 47. We're going to learn a trick so clever you might just forget you're doing math at all.
So, here's the first puzzle. Is the number 12,345 divisible by 47? Now, you could grab your phone, punch it into a calculator, or maybe you'd even start doing long division on paper. But hold on a second.
Because really, where's the fun in just getting the answer instantly? This whole explainer isn't about trying to replace technology. It's about peeling back the curtain to see the really elegant, beautiful patterns that are hiding inside the numbers themselves. It's about actually enjoying the puzzle.
So, let's learn our first move in this game. I like to call it the shrinking trick. The more formal name is the two-digit method. Basically, it's a way to take a big, intimidating number and shrink it down, step by step, into something way more manageable.
And to help you remember it, there's this handy little rhyme. Cut 2 digits off, that's all. Take the rest and multiply by 6, add them back, a clever mix. Sounds simple enough, right? Let's break down what that actually means. Okay, here's how it works in 4 easy steps. First, you take your number and you split it. The last 2 digits we'll call T, and everything else, the rest of the number, is A. Then, you just plug it into this simple formula, 6 times A plus T. If your new number is still a little too big to tell, no problem. You just do the whole thing again until you get a number that's easy to check.
This flowchart here shows you the whole process. We start with our big number n, run it through the formula to get a smaller number, and we just keep doing that loop, shrinking it down until it's tiny. And here's the really cool part. The divisibility by 47 stays the same at every single step. If the first number is divisible, the last one will be too.
So let's try this with our original problem, 12,345. In step 1, A is 123 and T is 45. We calculate 6 times 123 plus 45, and that gives us 783. Still a bit big. So let's do it again. For 783, A is 7 and T is 83. So 6 times 7 plus 83 gets us 125. Now we can ask, is 125 divisible by 47? Nope, not even close. And because the divisibility is preserved, we know our original number, 12,345, isn't divisible by 47 either. Pretty neat, huh?
Okay, that's a cool party trick. But you know us, we have to ask, why on earth does that work? Where did that multiply by 6 come from? It feels like magic, but I promise you, it's built on a really solid and honestly beautiful mathematical idea.
The secret is something called modular arithmetic. Now, don't let the name scare you. It's just the math of remainders. The easiest way to think about it is like a clock. On a 12-hour clock, 13 o'clock is really just 1 o'clock, right? The numbers wrap around. Well, in our game, we're working on a clock that has 47 numbers on it. And here it is. This is the secret key that unlocks the whole trick. In this special clock world of Mod 47, the number 100 and the number 6 are in the exact same spot. They are equivalent. Why? It's simple. If you divide 100 by 47, it goes in twice. And what's the remainder? It's 6.
I know this slide looks a little heavy, but the key idea is right there. We can write any number, n, as 100 times A plus T, right? But since we just said that in the world of Mod 47, 100 is basically the same as 6, well, we can just swap it out in the equation. That means checking our big original number for divisibility is the exact same thing as checking our new, smaller number, 6A plus T. That's the whole trick. We just transformed the problem.
But here's the thing about math and what makes it so fun. There's almost never just one way to solve a puzzle. That two-digit rule is great, but it's not the only rule. Let's look at another way to play this game, this time by just chopping off one digit at a time.
This method is pretty similar. Instead of 2 digits, we only take off the very last one. We'll call that last digit F, and the rest of the number Y. This time, the rule is to calculate Y minus 14 times F. And just like before, if this new number is divisible by 47, then you know the original one was too.
So which rules should you use? Well, think of them as two different styles. The two-digit rule is kind of slow and steady. The multiplication is easy, times 6 is no big deal, but it might take you a few more steps. The one-digit rule is faster. It shrinks the number much more quickly, but you have to multiply by 14, which is a little trickier. Neither one is better, they're just different tools for the same job.
Here are the proofs for both rules side by side. Don't worry about reading every single line. The important thing to see is that even though the details are different, one uses the fact that 100 is like 6, the other uses a trick with 140, the core idea is identical.
Both of these clever rules come from the exact same place, the beautiful language of modular arithmetic.
So we've spent all this time focused on just one number. What makes 47 so special anyway? Well, besides these fun tricks, it's got a few other quirky properties that give it a real personality.
For starters, it's the 15th prime number. It also lives right next door to a perfect square, 49. And this one's really cool. In that mod 47 world we were talking about, the number 46 acts just like -1. So if you multiply 46 by itself, you get 1. It's its own multiplicative inverse. How wild is that?
And that brings us right back to our very first question. Why go through all this trouble? Why learn these games and these rules when a calculator is always right there in our pocket? What's the real point?
Because the goal isn't just about finding out if 12,345 is divisible by 47. The answer itself is, well, it's trivial. The real goal is discovering the why behind it all. It's about seeing the hidden structure, appreciating the cleverness of the method, and, just enjoying the intellectual game of solving the puzzle. It's a great reminder that sometimes the best part of a journey isn't the destination, but the beautiful path you take to get there.